I changed my title. In fact, I didn't change my title. I never actually gave a title to the conference, and they gave the title that's in the program. This is what the title should be: Metrological Approach to Quantum Random Number Generation, and I will also talk a little bit about our implementation of a random number generator on a chip in an integrated platform. Okay. So I don't think I need to tell this audience why random numbers are important. What's interesting, perhaps, is that the needs that you have from these more classical topics also coincided in this project with the needs for a fundamental physics project for loophole-free Bell tests, and I will touch on that. But first, I will go back in time a bit. When I was a child, my father worked at the Rand Corporation, and he's an economist, and he had this book on his desk, 1,000,000 Random Digits with 100,000 normal deviates. And if you look inside, that's in fact what you see. You find 400 pages of random digits that were generated by the Rand Corporation in order to allow Rand and other places to do Monte Carlo simulations in the 1940s and 1950s. And if you look at this on Amazon, you will see it's a very popular book. It has 682 customer reviews. And in fact, some of those are very interesting. So this is the top positive review. It's a terrific reference work. It has so many great random digits. It's a shame they didn't sort them so you could find the one that you're looking for. Okay, so that's to remind us of something that I think we all know, said by John von Neumann. There's no such thing as a random number. It's not the digit itself. It's the process that produces them that is random. And the talk, in some sense, is about how to look more at the process in evaluating your random number generator and less at the product. Okay. I'm going to go a little bit farther with this. This is the publication P113 from June 1949 by the Rand Corporation that describes how this thing was made, and with this I will illustrate some important topics. So the way that this actually worked was they had a source of pulses that was running at a random frequency. I've not been able to figure out exactly how they made that or why they thought that was random, but let's take that as a resource. So that was producing many pulses per second, but with a random rate. And then they took a regular clock, 1 cycle per second, and they put those together in a counter so that the counter would count these until a stop pulse arrived from the clock, and then they would freeze this data and they would put it onto punch cards. Okay? And this was their way of generating one. It would give them 1 digit per second. Okay, punch cards. I don't know if you've seen punch cards. These are punch cards. Each punch card holds 50. It has 50 lines, each of which holds 1 digit. So in order to have 1,000,000 random digits, they had 20,000 of these punch cards. So this was then an important resource for Rand, that they had this warehouse of random numbers. Okay, and then they started looking at them, and what they saw was that although they started out random, so this is the ones that were taken in May of 1947, then after a month of running, they didn't do so well on statistical tests. Okay, and so you start to see some p-values here which are a bit scary, especially taken together. And so they decided that their random number generator worked well when it was tuned up, but that it could somehow lose its tuning and work worse. Okay. I'd like to point out that knowing how these things work, it's less likely that there was something wrong here in their original source. It's more likely that something was happening here. So for example, there was some interaction between the stop pulse here and the internal state of their counter. Okay? So converting something from an analog mode or from a physical mode into a data mode is an important consideration. Okay, so they saw that these things were not perfectly random, and what did they do? So we saw that it had a bias for odd numbers. It was now decided to re-randomize the table, or at least alter it by a little roulette playing with it to remove the odd-even bias. we added mod 10, the digits in each card, digit by digit, to the corresponding digits of the previous card. So this is their algorithm, that these are the digits that they originally generated. And then to generate the new stream of data, they add this bit with the 150 before it, and then so on and so on. And in this way, they generate a new sequence. Okay? It has the same information in it, just shuffled around. And then they conclude this was subjected to the various standard tests, frequency tests, serial tests, poker tests, et cetera. These million digits have a clean bill of health. They passed the statistical tests and have been adopted as Rand's table of random digits. Okay, so, and that's how we get this book with these random digits and these wonderful jokes that people make about them. That's my favorite one, actually, but okay. Okay, so okay, so in 1949, the strategy for generating physical random number generators was to make a device that you think should be random, and then apply statistical tests in order to decide whether it's random enough for your purposes. And then if it doesn't, if it's not good enough, then do some kind of massaging of the data until it does pass your tests. Okay, so this was 1949. Now, here in the modern era, we've improved some things a lot. So we now have random processes that we have access to random processes that we believe are absolutely random. We can use quantum processes. Okay? We know a lot more about randomness extraction, so it's not, there's a science now, it's not just guessing that something is going to improve the quality of your random numbers. You can actually get good random numbers from bad random numbers if you know how bad they are. Okay? And what hasn't changed very much is that frequency tests, et cetera, have been replaced by stronger statistical tests. That the methodology there has not changed in the same way that this and this has changed. We're still applying statistical tests in order to know whether the devices work. Okay? And I think it's pretty well known in this community that there are random number generators that do a good job with this and seem to do a good job with this and still fail these tests. Okay? So you can take a modern commercial quantum random number generator, and if you collect enough data on it, then you can find defects in it. Okay? And so we would like to do something better. We would like to do something that is not tied to the passing of the tests, and that's the methodology that I'm going to talk about. How much time have I used? Okay. Okay, so the new methodology is this. We're going to take a trusted process, which will usually be quantum, but let's just say it more generally. We have some trusted physical process. And it's going to be used in an analog way. There's going to be some instrument that is first using that process to generate some analog signals. And then that signal will be digitized. And then in the digitization process, which is also a physical process, we have to have a model for how that's going to work. But then at some point, what comes out of here is now in digital form, and it's passed through digital electronics that are somehow above any kind of suspicion. And so we can stop worrying about the problem at that point. Okay. In addition to the things that we want to have happen in here, we will also have some untrusted variables which will then have some effect on what comes out of this system. Okay? In terms of the assumptions that we're making, we're assuming here physics as it's known. So we're not suspecting that Maxwell's laws are wrong or something like that. And we're going to have to measure these, or we're going to have to do something which tells us how strong the effect of these untrusted variables could be on this process chain. And then finally, when we put all of that together, we'll get a model for the probabilities of our outcomes, which depend on these things, depend on this, but in such a way that we can put bounds on these probabilities. Okay? And assuming that the probability can't go to 1 or to 0, then we still have some randomness in that. And that's something that we can use, for example, in randomness extraction. Okay, so this is clearly not a device-independent approach. It's a very device-dependent approach, but it's inspired by some of the best device-dependent work that's done. For example, in precision spectroscopy, people are very good at quantifying their errors, both systematic and statistical, and when they give you a number, they can tell you a lot about why they think that number is correct and what the range of possible values it can have are. And that's the area of metrology, which is why I call this a metrological approach. Okay. So to give an example in terms of the canonical random number generator, so imagine I'm going to split photons in a beam splitter, and then I'm going to detect them with single photon detectors. And I would like this to be an equal probable process, so I put a 50-50 beam splitter here, and let's just say I'm doing this at a telecom wavelength. Okay, so now I look at what's happening here, and I will find, for example, that my 50-50 beam splitter is only 50-50 for unpolarized light. That is, averaging between the two polarizations, it's 50-50. But for one polarization, it's higher, for the other, it's lower. I will also find that my light source here actually has a range of wavelengths, but I can put some limit and say, well, I don't think it ever emits any photons below this or any photons above this in wavelength. And so then I can look at my curve, and I can identify, given the possible polarizations and the possible frequencies, I can identify the point where this works worst. Okay, so here, instead of having 50-50, I would have 2/3 and 1/3, but I would be able to say, if I've characterized everything that matters in the system, I would be able to say that this probability is bounded. Okay, and then I can say what the entropy of that is, and then I can use it. Okay, so this is the method. So far as I know, no one has done this for a photon splitting beam splitter, but in principle, you could do it. Okay. So why don't we do it? We don't do it because there are much more interesting methods for generating quantum random number generators. This is a phase diffusion technique where you take a laser. The laser naturally has a phase diffusion process, which is driven by spontaneous emission. So there's at least a part of that is quantum. With an interferometer, you can convert those phase fluctuations into amplitude fluctuations, which then can be efficiently and quickly detected by a photodiode. And since 2011, the records for speed of quantum random number generation have been held by this kind of technology. So, and they went up quickly for a while. So 1.1 gigabits per second in 2011. Then Huikwang Lo's group got 6 gigabits per second. And then we got up to 43 gigabits per second. Andrew Shields at Toshiba has either 20 or 80. They don't actually claim that this one is sufficiently randomized in phase to be random, but they still have some nice numbers. And then John Wei Pan's group has what I consider the current record at 68 gigabits per second. Okay, these speeds are, for practical purposes, fast enough that there's no point in going faster. It'd be very difficult to use that speed of generation. And so we're working on other things. I'll say a little bit about this publication where we implemented this kind of phase diffusion device on an integrated platform. Okay. So how does this work? First, you take your laser both above threshold and below threshold, and it's going to produce pulses of light, and those pulses in practice are going to look very similar to each other, but they will have random phases. And then you pass them through an interferometer, which has a delay that's equal to the delay between these two pulses, so that when they combine at this beam splitter, they overlap, and you can see an interference between them. And then you see an amplitude, which is a function of the phase difference between these two. Okay, and you can see this if I cut the interferometer so that I'm measuring just the pulses. They only have one way to get to the detector. Then I see these pulses, which when the current turns on, it does something messy, which is called relaxation oscillation, but then it settles down. And if I sample here, then this is the histogram of what I see. Okay, so this is many thousands of pulses which are overlapped with each other, and they all basically have the same behavior. Okay? And then I complete the interferometer, so now I have the interference, and what I see now has a whole range of different possibilities, and they have this distribution, which is a very interesting distribution called the arcsine distribution. It's what you get. The arcsine distribution is the distribution of the cosine of a uniformly distributed phase. Okay? It's like the projection of a circle onto a line. And it's what you get when you do interference, that you interfere light from the short path, light from the long path. This is the interference term between the two. And if this is uniformly distributed from 0 to 2 pi, then you will get the arcsine distribution. Okay. Okay. So, what is our trusted process? Our trusted process is laser phase diffusion. Let me tell you a little bit about how we characterize that. So we have a laser. It's a single mode laser. It's going to have a field in it. That field, if I put this on the phase space for the field, then it will have some value. And in the presence of spontaneous emission, which is always there if there's any gain, then it will get random kicks due to the spontaneous emission, and so it will randomly diffuse in this plane. Okay? The diffusion rate from laser theory is expected to be proportional to 1 over the number of photons that are in the cavity, and this is a well-confirmed result. So this is theory which goes back to the 1980s, and people have been working with laser diodes like this intensively. They've studied line widths extensively, and so we think that this theory is correct. Okay. Nonetheless, we can measure it. Okay, the figures didn't come out in the transfer. Nonetheless, we can measure it, and we see this directly. Okay. The more important thing here is actually we do have a lot of phase diffusion. The more important thing is that we're working with a cyclic variable, and this protects us against problems that you would have if you were working with a linear variable. So let me illustrate that. So the phase is going to diffuse, so that the phase difference between one pulse and another is going to have some Gaussian distribution. But as it exceeds the cyclic bounds, pi and minus pi, then being over here looks the same as being over here. So we have to take this part of the probability distribution and stick it here, and this part and stick it there. Okay? And so now you see that as it diffuses, it's going to very quickly fill up these regions, and we'll get a flat distribution. And in fact, you can see the error relative to a uniform distribution drops off very quickly. It's faster than exponential with the amount of diffusion. Okay? And in fact, here we have tens of pi of diffusion, and so the error is completely negligible. Okay? Even better than that, using a cyclic variable, if some other effect comes along and shifts our phase, then it will shift this distribution. It will shift this distribution also after we've used the cyclic property, but it doesn't change what the error is. Okay? Put that another way, if my process that I trust has randomized this distribution of a cyclic variable, then there's nothing that you can do that will give it anything other than a uniform distribution. Okay, so we don't have to worry about things affecting our laser and affecting it. Okay. Okay, good. Analog physics. So we've got this interference. When we include the finite speed of the detector, then we get a visibility here, and we get a number of noise sources. And in terms of the metrology, what's important is that we can measure all of these. So I show you just one. This hangover error, this is not because the operator drank too much the night before. This hangover error is remaining signal that came from previous pulses. So we can see that if we put in a chain of pulses, and then there's a last pulse. The last pulse has nothing to interfere with, and so we get a signal here that does not have this interference in it. Nonetheless, you can see here there's some extra variation which is left over from these. So that's ringing in the detector. Okay, but we can quantify that, and we can see how much noise there is. Okay, we can measure all of these things. Finally, the digitization, that we put this into a comparator which has a reference level. Maybe you can see some colors there. This, if the voltage is above the reference, then it's a 1, otherwise it's a 0. Okay, that can be affected by these noises that I just described. It can be affected by noise in the reference level. Again, we can measure all of these things. what's interesting is because of this arc sign distribution, we can have a simple analytic expression for the probability to have a 1 in function of the noises, and this is the width of the signal here. Okay, and all of those are observables. Okay. So then we have an upper bound on this, we have a lower bound on this, that gives us an upper bound on this probability, which is what we need in this application. Okay, in fact, the error is 12% relative to the ideal 50-50 case, or we have 0.83 bits of min entropy in this under assumptions. So the bound that we take, the noise contributions that we see are in fact normally distributed. They're things like Johnson noise. But if we take 6 sigma as our bound, so that we can say that the assumption that it's within this bound is wrong less than 1 in 10 to the 7, then we get this. Okay. So having this device working, we published on this in. We had this working in 2014, and then we were approached first by NIST because they were working on a loophole-free bell test, and then once we started working with NIST, we advertised this to other groups, and the groups in 2015 that were doing these tests, they said, yes, we definitely need something like that. We need some kind of random number generator that is going to have bounded errors and that is able to work very fast. Okay, so in that way, we got onto this paper. So there's me, there's Carlos, Valdemar, Valerio. We also got on these papers to explain a little bit what's going on. In a bell test, you have a short time window in which you would like to make your decision about what to measure. You have to worry about the possibility that your random number generator is influenced by prior conditions, because those prior conditions can be time-like connected to the distant particle. Okay. And so our solution to this was to take the random number generator that we had, which had a known min entropy, to incorporate a randomness extraction, a very simple randomness extraction, which just computes the parity of multiple bits. And then we can stuff a number of events in here, calculate the parity, and reduce this error to the levels that were needed by the bell tests. Okay, that's this device. It got us into these papers, got us into the cover of this. So here you can see Valdemar. I guess you all know this cover, right? This is John Bell, and these are all faces of famous physicists. And for some reason, Rupert Ursine appears about 20 times, and other people appear once. But okay, so Valdemar is here. Carlos is here. I was looking for myself. I really wanted to be in John Bell's beard. I thought that would really be the appropriate place for me. I was not in John Bell's beard. I figured maybe I could be in his 1970s era tie, which is a very attractive thing. I wasn't there either. It turned out that I was up here in John Bell's lush 1970s hair, which, looking at me and looking at John Bell, I think means that Physical Review Letters has an ironic sense of humor. Okay, so implementation on a chip. So this is something which came out in Optica in 2016. Unfortunately, the images are not very good. This is a zoom in of the device. Let's see if this is going to get any better. No, this is not going to get any better. Okay, so this is a zoom in of the device. There's a laser here. There is a Bragg grating here to provide external feedback and thus to tune the laser. Then what you have here is waveguides which bring this laser output, and there's a second laser here to a multimode interferometer. Then the interference is detected by these photodetectors, which then go off chip and are digitized. Okay. So we're okay, so this laser is running continuously. This laser is gain switched, which is to say that this is pulsed so that it experiences the strong phase diffusion effects that happen below threshold. And then they are tuned so that they're similar in frequency, and then they interfere. And you can see this, I hope, when there's a pulse of injection current, then due to temperature effects, the frequency of the pulsed laser is going to sweep. And you can see that in the beat note between them, which goes from a moderate frequency to a near zero frequency, and then goes back up as the frequency of the pulsed laser crosses through the frequency of the continuous wave laser. Okay, and so here is a good place to sample, and if we sample there, then we see again an approximation to this arcsine distribution. What's happening here is that the signal from the interference is relatively weak. It's not as strong relative to the noise as in the macroscopic version. I can't explain why this is. Okay, sorry. So there are solutions to that, and we are going forward with this integrated version. Okay, so in conclusion, I've described a methodology for rigorous experimental characterization of random number generators, something which I hope provides a more trustworthy assurance that these things are actually giving you bits which come from a quantum source, or rather that give you assurances of the amount of entropy that you're getting from a quantum source. These things can work at very high speeds. Our record is 43 gigabits per second. I've shown integration in indium phosphide using a two-laser strategy. And I have to say, we're working now on the metrology for the two-laser strategy. Okay, so I think that's it. And I thank you for your attention, and I thank everyone who worked on this project. It was a collaboration between my group, me in my group, members of Valerio Pruneri's group, especially Carlos Avellan, but also people from Valencia who contributed to the photonics work. Okay, thank you very much.